Well, there's there's a lot of people in here right at the start. We're very excited for this. This is a topic we've definitely been wanting to cover, so we have quite a lot of great info for you today. But you know what? Let's go ahead and get started. So my name is Cody Cole. As it says on the slides, I am the Nuclear Product Manager at Berkeley Nucleonics, and I am joined by Managing Director Paul Schotanus from Scionix. Some general comments before we start this webinar. If you are having technical difficulties, there's 3 things we recommend. Please use the updated Chrome browser, disable any VPNs for the duration of the presentation, and make sure that the browser tab for this webinar is not currently muted. Besides that, if you do miss any content of this webinar, we offer playback videos on YouTube following their completion. So definitely no worries if you miss a few of the slides. To explain our companies, Berkeley Nucleonics, we have been in the industry for over 50 years. We do RF and microwave testing and measurement equipment, and of course, nuclear spectroscopy. Scionix manufactures state-of-the-art scintillation detectors, and we are doing this webinar. This presentation is a part of our nuclear webinar series. Our goal here is to produce content related to a variety of topics in the fields of nuclear spectroscopy and radiation detection, using our valuable industry experience to help define concepts and technologies. But without any more from me, I'm going to let Paul take the floor, and we'll get this presentation underway.
Thank you, Cody. Welcome to this webinar on neutron detection with scintillators. I'm Paul Schotanus at Scionix. Today, I want to give you an overview of the state-of-the-art of materials we can use in our sensors to design scintillation detectors for neutrons. I will first briefly discuss the method of interaction between neutrons and scintillation materials. And I'll discuss what different ways of this interaction we can use in our scintillators to design the detectors. Many fields exist where neutron detection actually is very important. And I don't think that in this 45 minutes we can touch all existing materials. But I will discuss today all materials that are commercially available and that we can use in our sensors. At the moment, there's a lot of research going on in new, innovative materials that in the future may replace existing materials. We hope in the future also to be able to use those materials, but at the moment, the state of the art is what I'm going to present tonight. Neutrons are little funny animals. They have actually no charge, the mass about the same as the proton, and because of this, they have almost no interaction with the electrons of materials, but interact only with the nuclei. Because of this, they penetrate much deeper in matter than, for example, X-rays. Energies from neutrons can vary between a fraction of an electron volt to many, many MeVs. An example of neutron detectors is, for example, to look at the quality of nuclear fuel rods. You see at the left there a picture. Those are organic scintillators. And the application fields vary a lot. In nuclear physics, for example, we have reaction products, particles, also neutrons. We'd like to know the energy and the flux. As I said already, in fission materials, uranium, plutonium, neutrons are emitted, and we'd like to be able to detect those for special applications. Neutrons interact in a totally different way with matter, and that means that the biological factor for neutrons is much higher than for gammas. So in mixed radiation gamma fields, we like to know what kind of neutrons I'm measuring here and how many gammas are there. Neutrons are also emitted by so-called special nuclear materials, highly enriched uranium, plutonium. Because we like to know where those materials are, control them, identifiers and other detectors contain neutron detectors. They are crucial for many security applications. And in industry, non-destructive analysis, special properties of neutrons allow us to see, for example, the lithium motion in fuel cells. And that brings me to our first poll question, actually, Cody. the question, in what kind of application are you active? You who was listening today to this webinar.
Of course. So if you are currently watching, there is now a poll up on the screen. Simply fill in your answers and we'll go ahead and see where everybody sits. Oh, wow, that's a lot of answers. Looks like health physics and physics research are winning out right now, Paul.
Yeah, but we see in all the fields there is a significant amount of people who work on this subject.
Yes.
And this is only a few subjects. There are many more applications. Actually, the field of neutron physics is extremely wide. We're only scratching the surface here today. Okay, this is great to see. Thanks very much, everybody.
And here are the results.
Yeah, a lot of health physics. Okay, right.
A lot of health physics and physics research.
Yeah,
so
perfect.
Going back to the slides.
Yeah. So neutrons. Neutron energy can vary, as I said, between fraction of an electron volt to many, many MeVs. To give you a little of an idea, a neutron source like Californium-252 has an average neutron energy of about 2.5 MeV, whereas a plutonium americium, beryllium americium source, the energy is a little higher, 4 to 5 MeV. Neutron generators can generate very high neutrons. Actually, it's a particle accelerator. Energies can be up to 18 MeV. Neutrons can be thermalized, slowed down to low energies, to thermal energies for high-density polyphene moderators, and realize the speed of a thermal neutron is still 2 kilometers per second. Neutrons are not particles we can put in a jar, so to say. They're actually unstable, undergo beta decay. So neutron energies can vary between thermal energies to many, many MeVs. We speak about fast neutrons when the energy is more than roughly 50 keV. The interaction between neutrons and matter with the nuclei is actually twofold. First of all, via scattering to mainly proton-rich materials, or via nuclear reactions. Today, I will discuss both those interactions separately. First, we'll go into details, what scintillators can offer us in scattering interactions, and the second part of the presentation will be about nuclear reactions. You see here a list of the energies of the neutrons, low energies up to many, many MeVs. To give you a bit of an idea about interaction of fast neutrons in materials, we still need a significant amount of material to absorb neutrons of roughly an MeV. Neutrons can transfer energy to materials by bumping into hydrogen-rich, bumping to protons, and transferring energy by elastic and inelastic scattering. So a very good neutron absorber and scintillator actually is a regular plastic scintillator or an organic liquid. But when the neutrons are absorbed in organic materials, they produce a continuous energy spectrum. To the left, you see a spectrum of a neutron in an organic material. You see there are no peaks because the energy transfer results in this continuous spectrum. Gamma rays, when interacting with organics, mostly via Compton interaction, and also there we see a continuous spectrum. You see the Compton edge of the material there. So by looking at just the pulse height of a scintillator, we cannot discriminate neutrons from gammas in a simple way. And important to separate neutrons from gammas is that we need to use different tricks. We have to use looking at pulse shapes. You have to look, for example, at the geometry of the material. And this way we can separate neutrons from gammas. And that's very crucial in use of scintillators. And that brings me to the most classical, simple, fast neutron detector that is around, which is actually a powder of zinc sulfide in a polymer plastic matrix embedded in rings of plastic. This is a classic fast neutron detector. LGM manufactured this called EG410. It exists for over 60 years, I think. The mass of zinc sulfide here in these rings is very small, so there is very little gamma interaction. But neutrons that actually are passing through the perspex matrix rings hit the protons are accelerated, and they hit the zinc sulfide and give you light pulses. The efficiency of this detector is not extremely high. It's of a fraction of a few percent because we can't make those rings extremely thick. It's only about roughly half an inch, a little more, 16 millimeter actually. When we couple such a scintillator actually to a light detector, which can be a regular photomultiplier tube or a silicon detector, we see a continuous spectrum of neutrons to the left there. And the gammas have a very little interaction in the zinc sulfide, and we see only a very small amplitude. So this very classical detector is an extremely easy way to measure the flux of fast neutrons with a very low gamma sensitivity. Another material that is a very efficient neutron detector are organic liquid scintillators. A specific property of materials is that, of liquids, is that the pulse shape is different from neutrons and for gammas, which means that if we can monitor the pulse shape that actually exists when one neutron or a gamma is absorbed in a scintillator, we can say, yes, this is a neutron or it's a gamma. With a light flash, you should see that when there's one neutron absorbed, there's a number of photons emitted. The intensity rises up and then slowly rises down. These times are in the order of nanoseconds, tens of nanoseconds. But the shape is definitely different for a gamma than for a neutron for many materials, many liquid scintillators. Liquid scintillators are known already since 1960, and a very old-fashioned name is actually Ne213, which is the same actually as EG301 or BC501A. These materials are all xylene-based. Xylene is a solvent. Actually, also organic crystals, like stilbene, anthracene, or parathephenyl, have been around for over 50 years. It's interesting to know that these materials are slowly getting rediscovered by the requirements in neutron detection over the last years, and at the moment, stilbene crystals are grown in the United States on a commercial scale up to large diameters. I'll touch on that a little later in the presentation. A liquid cell actually looks very simple. It is a piece of metal where the liquid is enclosed in with a window. And looking in this way at pulses from neutron and gammas by scintillators is called pulse rate discrimination. Liquid scintillators, organic liquid scintillators, have some disadvantages. One of the disadvantages is that they expand quite strongly as a function of temperature. And this means that we have to find a way this material can go to when the temperature changes from roughly, let's say, 0 degrees to 50 degrees, which can happen in environmental conditions. There are several solutions for this expansion problem. We can have an external expansion reservoir, like you see in the picture in the center of this slide. Or we can have a specially shaped optical window that actually dips in the liquid. We call this dip-in window. And the nice thing about this shape of optical window is that in all orientations of the detector, we always can have a good optical contact with the liquid. Of course, you can also put less liquid in the cavity, but then it means that in some orientations, you have no optical contact and you lose pulses, lose amplitude and quality of your detector. At the right, you see how such a liquid scintillator can look like, for example. This is a big one of 1 liter. A big photomultiplier tube, or these days we can also use silicon solutions. And this detector has a very low mass of the housing. The thing is that many of these old-fashioned liquid scintillators are flammable and have a very low flash point and are also toxic. On a liquid scintillator, there's always a finite chance of leakage. And this is something, of course, that we have to realize. Slide. And therefore, I'd like to go to my second poll question to your participants. Is anybody of you using still low flash point liquid scintillators?
Okay, here we go. Poll is up again. Let's go ahead and see.
That's good.
While the answers are coming out, for those who are not sure, what would be a good way to determine that, Paul, if possible?
Looking at the label, what the label of the detector says, because I will get that in the next slide. Low flash point liquid scintillators are becoming more and more problematic.
All right.
Oh, you see about 34. Okay, right. I see. Yeah.
Going to end in about 10 seconds here. So if you want to get your answer in, go right ahead. All right. I see that David Weaver is using a solid state detector instead.
Good. Okay. Thanks everybody for replying to this question. We still see that there's a significant amount of people use actually a low flashpoint liquid scintillation cell in their laboratories.
Oh,
yeah.
Yes. Sorry. Hopefully, so it looks like the header for this quiz was for scintillators, but basically, I'll go ahead and sort it out. But thank you for your answers, everyone. Let's go ahead.
Yeah, go ahead. Okay. So the fact is that low flashpoint liquid scintillators are becoming more and more of a problem in many laboratories. And I have, that's the bad news. The good news is that there are these days replacements for low flashpoint liquid scintillators that have a much higher flashpoint and quality-wise are almost just as good in neutron gamma discrimination. And this is something I want to touch in the next slides. At the moment, I still want to show you one picture here that the liquid scintillator actually, we can actually also add boron to the liquid to enhance the sensitivity for thermal neutrons. It's just a slide that shows you some pulse scatter plots. Let's go to the next slide. And there, actually, I'll show you the properties of an old-fashioned high flashpoint, low flashpoint scintillator 301, and the 309 alternative we have available these days. And actually, the performance is quite comparable. And we are trying to convince the community over the last years to move to high flashpoint scintillators, because actually it's much less of a problem in terms of safety in your laboratory and also in terms of transport. So EG309 is a scintillation liquid which is specially designed for neutron gamma discrimination with a high flashpoint, low vapor pressure, and besides that, it's not toxic. And this removes a lot of worries from the safety people, of course. The performance is almost comparable to the flammable type of liquid. You see at the bottom here some performance figure of merit numbers. Get to that a little later. And actually, we see many people are fully satisfied with the performance of EG309 in their detectors. So liquid scintillators are very well suited to do neutron gamma discrimination. And the use of these devices actually is helped greatly by the available of digitizers. Digitizers are advanced pulse shape analysis units that actually can give you directly an answer whether you have a neutron or a gamma in your detector. This was not possible in the past, but at the moment those things are readily available, made by several companies around. And actually what we see in those digitizers, the results are that we see scatter plots there, like you see to the right. One of the clouds are the neutrons, the other ones are for the gammas. And by setting a threshold, we can see that down to quite low energies, we can very clearly discriminate the neutrons from the gammas. The nice thing about liquid scintillators is that they can be made pretty large. We have made them up to 50 by 50 centimeter, segmented into 4 pieces. And it's a well-established technology at the moment. Many geometries, some pictures, helps you to understand. At the left, for example, we see a quite large liquid cell, about 250 millimeter in diameter. We use a photomultiplier tube because of the speed, but also a tapered geometry like you there see in the middle. The square geometries we can use to stack them into walls, neutron detection walls. And the pipe shape we can use, for example, to create configurations like you see there to the right. When we speak about neutron gamma separation, we often speak about figure of merit. So the figure of merit is actually a number defined by the formula. You see that to the left. How well can you separate the neutron cloud from the gamma cloud in those scatter plots? Figure of merit deserves some comment because it's not a holy number written in stone, because it depends on a number of parameters. It depends, first of all, on the scintillator. How much are the pulses actually different from neutrons and gammas? Furthermore, it depends very strongly on the quantum efficiency of your light detector. So how good of a photomultiplier do you have? It's really a big difference. The geometry, if you have a smaller photomultiplier than the liquid cell, you need to use a light guide. You lose a little light, you lose a little statistics. This degrades the figure of merit. Not to forget, the energy of your neutrons is also very important. If you use high energy neutrons, the separation is much more easy than when the energy is lower. The quantum efficiency of the photomultiplier tube, or the PDE of the silicon detector, actually plays a very important role. The difference in the figure of merit can be up to 30% even. Because figure of merits for neutron gamma separation depends so much also on electronics, and all these other parameters you see here, they're very difficult to compare from one setup to the other setup. So if you read in the literature figure of merit numbers, you have to look very careful what people actually have used to compare it to your data. There exists a great variety of liquid scintillators. We can even have scintillators with deuterium in them, where we replace the hydrogen by deuterium. We can load them with boron, like I earlier showed you a scatter plot. And we even can load them with gadolinium. We'll show in the section where I'll be talking about the interaction with nucleus that gadolinium has an extremely high neutron cross-section. But gadolinium loading in liquid scintillators is by far not that easy. And actually, when you go over 1%, the material becomes unstable and doesn't remain in the liquid. So it is possible, but you have to be careful. So we briefly touched the organic materials, the liquids, and the pulsar discrimination. And like you earlier showed you that there are other organic materials that show an extremely good neutron gamma separation via pulsar discrimination, like steel beam, for example. I'd like to show you some pulse scatter spectra here, where you see the PSD spectra from a steel beam crystal, and that's actually much better than a liquid scintillator. Steel beam crystals got some renewed interest recently. They're produced at industrial scale, grown from solution, but they can be made extremely large, and they are quite more expensive than liquid scintillators. Steel beam crystals are not hygroscopic, but they are quite sensitive to temperature and shocks. But a steel beam crystal, especially in a small size, can be a very nice alternative to a liquid scintillator because the material, of course, is not liquid. You can put it in a housing much more easy. There's no need for expansion. And together with the right light detector, you can make very small, very efficient scintillation detectors that can separate neutrons and gammas from gammas very nicely. Now to the most recent developments on plastic scintillators. Actually, it was always a dream from the physicists to have a plastic scintillator that could do neutron gamma discrimination. And until a few years back, actually, this was not possible. If you look to a regular EG200 scintillator or NE102, the old-fashioned name, there's absolutely no difference in the pulse shape for neutrons and gammas on a regular plastic scintillator. But these days, we have plastic scintillators produced by Elgen, EG276, that do show you this neutron gamma separation by pulse shape analysis. We have two versions, a green one and a blue one, and these days they can be made up in cylinders up to about 5 inch in diameter, and plates up to about 10 inch by 10 inch. Of course, the advantage of a plastic scintillator that can do pulsar discrimination is that there is no expansion need, it's much more convenient to handle, and so on. Properties you can find in the tables, you can calculate the cross-sections for neutrons, it's quite comparable to the other organic materials. The pulsar discrimination is almost as good as EG309, which is a liquid scintillator, but for most applications, it's absolutely sufficient. There were some very nice recent publications about this that show you the scatter plots and the figure of merits for EG276 scintillators. The only thing is, it's advised to use the material to be sealed from air, because there are indications on the long term the material loses a little transparency. EG276 can be read out using silicon photomultipliers, and we can also do pulsar discrimination for a smaller size of samples. Interesting is that also these days we can actually dope plastic scintillators with lithium, lithium-6. And because Here, the plastic scintillator actually acts as the moderator, means the neutrons are being slowed down in the material, so they can undergo a nuclear reaction with lithium-6. We see a peak there of the particles that exist that result from this nuclear reaction, and the peak shows up at quite high energy, about 380 keV. And this allows us actually to enhance the neutron sensitivity of the plastic scintillators. So up to now, I talked about neutron detection via scattering and inelastic scattering in scintillators. The other way to detect neutrons in materials is actually via nuclear reactions. This only works if we slow down the neutron to thermal energies. So actually they can undergo this reaction. The neutron capture, I show you the formulas here in the left block for helium-3. Of course, this is not a scintillator, but it's the most famous neutron detection gas, as I'll show you later. Boron-10 and lithium-6. In all those cases, we produce particles. And the nice thing with a particle is they can be fully absorbed in the material. And this gives us, in the end, a peak in our spectrum. At the right, you see the cross-section as a function of a neutron energy, as a function of the neutron energy of those different materials, helium-3, boron-10, and lithium-6. There's also a reaction based on gadolinium. Gadolinium actually has the highest cross-section of all materials for neutrons. But this is a neutron gamma reaction. So we are not producing no particles. So the gamma rays of several energies are absorbed in the material. And the analysis of the spectra is not so straightforward. In spite of this, for some applications, gadolinium scintillators are very an interesting option. The most common neutron detector, as everybody heard about it, is a helium-3 counter. Helium-3 tubes, pressurized up to 3 to 4 bars, is a very unproblematic gas counter. It's easy to operate. There are no special electronics needed, except high voltage, of course. It has a very good neutron gamma rejection factor. There are no serious safety issues, except that it's a pressurized tube. So you have to be careful when taking this on airplanes. That is allowed. You can manufacture helium-3 counters up to really large diameters, up to, let's say, 2-inch diameter and 1 meter long. But there is a worldwide structural helium-3 shortage. There was a moment, this was called actually helium-3 crisis. At the moment, it's not so imminent, but it's still available. But there is a cost issue and availability issue of helium-3. Helium-3 actually is the ideal neutron detector with a very low absorption chance. But there are alternatives these days in the form of scintillation options. So my next question, actually the last one, is do you think there are scintillators that can be used for neutron detection as well as high-resolution gamma spectroscopy?
All right, Paul, and also something had happened with the last poll, so we also have a makeup question on here for the low flashpoint liquids. But go ahead and feel free to answer both questions. Once you answer the first question, you can navigate to the next one. At the bottom of the presentation screen, there is the next button. All right, looks like everybody found it. There we go.
This is better than the last poll.
Yes, it looks like either the titles got duplicated, but quite all right. We're making it up now.
Good.
Go ahead and let answers go for about 10 more seconds. And all right, I'm going to go ahead and end the poll.
Okay, well, this poll, the outcome actually of the low flashpoint liquid question is actually that we see that the number of low flashpoint liquids anyway in the audience tonight is slowly decreasing, which is a good sign. It's good, but still good to know these numbers, yeah.
Yes. But back to the presentation.
Yeah, but where is the... Yeah, there we are. Okay, good. For neutron detection in helium-3 counters, we need to thermalize the neutrons, of course. Otherwise, they can't undergo the nuclear reaction. You moderate neutrons by absorbing in high-density polythene So they can be moderated, and then they can be detected in your slow neutron detector. You should realize that the natural abundance of boron-10 is 20%, and that's the material you have the nuclear reaction on, and the abundance of lithium 6 is a typo there. It's 7.6%. 7.6% of natural lithium is lithium-6. We can use enriched lithium-6 scintillators also. So lithium-6 containing scintillator is a very efficient thermal neutron detector. And there are some materials around here, for example, lithium iodide. Lithium iodide is a scintillator that has a neutron peak at a very high energy of roughly 3 MeV, because the excess energy for the triton and the alpha particle is 4.8 MeV. And this means that if we use a small lithium iodide crystal in a neutron gamma flux, and there is the neutrons are thermalized properly, we see a thermal neutron peak at about 3 MeV, very narrow, about 5% width, and we can separate those very nicely from gamma rays. Disadvantage is that lithium iodide is not offered in really large diameters, large sizes, and it's a very hygroscopic material, difficult to grow, but 3 mm of thickness is sufficient to 95% absorption of thermal neutrons. But in, for example, neutron dosimeters in bonospheres, we can perfectly use tiny lithium iodide crystals coupled to, for example, silicon photon multipliers to replace helium-3 tubes. Another neutron scintillator containing lithium-6 is lithium glass. Lithium glass is also cerium doped. It's a fast scintillator. It's much faster than lithium iodide. And it's poured, so it's not really grown like a crystal. We can't use this material in extreme large sizes, but we don't need that, because actually 90% of the thermal neutrons are already absorbed in 1.5 millimeter of material. The fact is that the excess energy of the reaction is very high, but unfortunately the ratio between the alpha light produced by the alpha and the gamma ray is very low in this particular glasses, in general glasses. So it means that the thermal neutron peak will only show up at the energy at about 1.6, 1.8 MeV, which may interfere with present gamma rays, natural gamma rays. Still, this material is being used in, for example, applications where we want to have detection of neutrons at the same detection as the same do fast timing, because the decay time of a scintillator is relatively fast, roughly 60 nanoseconds. And actually, I think now my next poll question should come up. Yes, before this Cody, the previous poll question on the high resolution is something that should come now.
Oh, that was answered in this quiz. Paul.
It was answered already. Okay. No,
yes. So it was, yeah. So it's right here.
It's okay. It's okay.
Moving on.
Okay, we move on. Anyway, back, please. Thank you. We move on to the next scintillator that can offer us as well a very good gamma resolution as a neutron sensitivity, the CLYC family, which is a relatively new scintillation material. We call it CLYC, cesium, lithium, yttrium, chlorine, doped with cerium. So the more better the scintillators get, the more complicated the names become these days. We see here a material that has a quite nice density. It is a proportional crystal, like I showed you in the other webinar on high resolution materials some time ago. So that means it can have a very nice gamma resolution of roughly 5%. But also, because it contains lithium, we see a very nice clear lithium peak at about 3 MeV, a neutron peak at 3 MeV. The light output is quite good, 20,000 photons per MeV. And we can actually have quite large size of crystals these days. And this is an example of a material which we can detect neutrons and gammas at the same time with a very good energy resolution. So CLYC is a material that's ideal for small identifiers and personal radiation dosimeters. Actually, in CLYC, we can also do pulse shape discrimination, like you see to the bottom right. There's an example of a scatter plot there for neutrons and for gammas, where you see that the neutron cloud is very nicely separated from the gamma background. So we can separate neutrons from gammas in this material as well by pulse height analysis as by pulse shape discrimination. Actually, also with CLYC, we can do fast neutron detection because there is a finite efficiency for the chlorine-35 reaction on neutrons. So it is possible to do this. And some people actually are using this capability. You need a little more material for it. We need more length than half an inch. We need to 90% absorption for thermal neutrons. But this is an option for CLYC. I just want to mention. And this brings us to our last, most recent development on high-resolution crystals with neutron capability. Cesium, lanthanum, lithium, bromochloride, CLLBC. It's a mouthful. Quite nice density of 4.8. It's a fast scintillator, very bright, even almost the same brightness as sodium iodide actually. It is hygroscopic, but that's not the main issue. It has lithium enrichment, and actually we can reach a very good energy resolution there, less than 3.5% full width half mix at 662 keV. The next slide shows you some spectra of this new material. You see the cesium spectrum. It's a very nice, sharp 662 peak. There's a table there with some other resolutions because it's so bright. Also at low energies, 122 keV, we can have resolutions of 6.5%, which is quite good. And the neutron peak at 3.1 MeV is extremely sharp with a width of roughly 2%. These materials are available up to 3-inch size in various thicknesses. There is a difference between all these scintillators in neutron efficiency because of the amount of lithium they contain. I earlier told you that for lithium iodide, we need about 3 mm to 90% absorption of thermal neutrons. Lithium glass, we need about 1.5 mm. And these materials, we need about 12.5 mm, roughly half an inch for the same number. Also with CLLBC, we can do pulsar discrimination on neutrons and the gammas. So this new material is really quite interesting to use in a variety of applications in new generation identifiers, and offers us a great of advantages compared to classic materials. Next, I would like to mention a few special scintillators. One special scintillator is pressurized helium-4. It's not a liquid, it's not an organic material. It is a gas, but at the same time it's also a scintillator. This is a rod actually of a few hundred bar helium-4. And this actually is a UV scintillator. There's only one company who makes this kind of detector so far I know, which is Arctis in Switzerland. But it's interesting to mention because these kind of detectors can be actually made fully low power, powered by low voltage, because the scintillation can be detected with silicon photomultipliers. You only have to live with a pressurized bar, but for the rest, the efficiency for neutrons is quite good. And then we have gadolinium scintillators like GAGG. They look nicely yellow because the emission is in much higher wavelengths than the blue scintillators we saw up to now, or the green plastic scintillators. This is a very, very efficient neutron scintillator. However, the neutron reaction consists of gammas, and it depends totally on your application, and this is something you really can live with for your neutron detection. Yeah, in the organic scintillator part, I didn't discuss the boron-loaded materials. It's possible to load boron in plastic scintillators called EG254. Up to 5% natural boron can be added in the form of organic boron compounds. Means we have 1% boron-10. This is also a particle reaction with boron. And the neutron peak, the thermal neutron peak, shows up at energies of roughly 76 keV. Again, here the neutrons, the fast neutrons, can be thermalized in the material and then undergo a nuclear reaction with the boron-10. Here are some properties of this material, and this may, depending on your application, also be an interesting option. Of course, this blue scintillator can be read out with regular light detectors for a multiplier tube or silicon-based solutions. I already discussed the requirement for large neutron detectors, large replacement for large helium-3 counters. There is these days a material that is a mixture of lithium fluoride and zinc sulfide called EG426. It's It's a white sheet. At the bottom there, you see how it looks like. It's a powder, pressed powder, with a thickness of about 0.3 to 0.5 millimeter. And these materials are quite efficient thermal neutron detectors. The efficiency is 30% to 50% even, in 0.5 millimeter thickness. They emit blue light. In the middle, you see the emission. And they are made in sheets up to real large sizes. The fact is that with a sheet scintillator, the problem is to get the light to your light detector. If, for example, you have a big slab, you like to put your light detector somewhere at the corner or at the bottom. And the solution for this is to use a wavelength shifter. And a wavelength shifter is a material that actually is excited by blue light and emits green light. So by pushing this 426 material on both sides, possibly, of a wavelength shifter, we can actually make a very efficient neutron detector that works up to real large dimensions. Here you see a spectrum of alpha particles in zinc sulfide. Actually, this is a number of the photon flux we have calculated. And to the right, you see a comparative spectrum of a 426 spectrum. And that zinc sulfide screen, very common scintillator for alpha detection, is actually very thin. And this material 426 is much thicker, 0.3 millimeter. This one is 0.3. And you see there is still 1/3 of the photons coming out of this thick sheet. And this is way sufficient to lead via our wavelength shifter to our light detector. And you see there how it looks like there. You see a blue sheet there. That's the blue scintillation light of the 426 induced by neutrons or whatever. And we see then the green light coming out of the corner. In that location, we can put our light detector, whether for a multiplier tube or a silicon device. The top right, you see how these things look like. The grains, you see that the particles have to travel the distance from one grain to the other, of course, and not being absorbed in the binder, because there's some way you have to keep these powders together. But still, this is a very interesting solution that's used more and more to replace large area helium-3 counters for neutron detection. So you see a pulse height spectrum here. It's not a very exciting pulse height spectrum, no peaks there, just counts. We're just counting the neutrons. But you see when you irradiate these 426 detectors with a gamma ray, an intense gamma ray, you see only a very small amplitude. So by setting a threshold, you can very easily discriminate the gammas from the neutrons. There are solutions that work with a full multiplier tube, like you see in the bottom here, but also we can use silicon photon multipliers to detect the scintillation light from the green wavelength shifter. And actually, we have been successful in replacing small helium-3 counters by these 426 sheets and wavelength shifters read out by a few tiny silicon photon multipliers and getting the same performance as with a helium-3 counter. So this is a nice example of how this kind of solution can replace helium-3 counters in, for example, nuclear identifiers. And that brings me to my final remarks. I hope I could be able to show you several scintillation options for neutron detection and neutron gamma separation. These days, neutron gamma separation from scintillators is much more easy than it was in the past, because we can use digitizers that are these days readily available from several manufacturers. There are several lithium-based inorganic materials that can offer us, beside good neutron sensitivity, also an extremely good gamma resolution in our scintillation detectors. And I demonstrated you that lithium fluoride zinc sulfide screens can read out by silicon photon multipliers to actually replace helium-3 tubes also in radiation portals. Thank you.
Thank you, Paul. So that is the end of the presentation segment of the webinar. Before we get into the question and answer area of it, I would like to mention that if you would like additional supporting materials for thermal neutron detectors, we do also offer another format. That would be our BNC Academy, which has different videos, lessons, and so on that you can participate in. If you would like to check it out, the link is right there, or feel free to contact me and I'd be happy to provide personal info on those courses. But moving on. Paul, I do have some questions actually that were asked during the presentation that I would like to forward to you.
I saw one that caught my eye. It is a question that if the natural background from lanthanum in the lanthanum compounds influences detection sensitivity.
Right. That is a question from Susan Smith.
Yeah, I can answer that this way, that if you're talking about the detection sensitivity for gamma rays, of course, the presence of the lanthanum background does influence the minimum detectable activity. On the other hand, the neutron peak is so away from the natural background that this is not really an issue for the neutron sensitivity.
Right, excellent. I do have some questions here regarding slide 16, this comparison. The first one is from Neil Brown. And Neil Brown was wondering, how vigorously have the new technologies in liquids been validated and calibrated against older materials? So he's wondering, between the old and the new, how much work has been put into
there is a considerable number of publications that have compared 301 and 309. And the outcome is that there is a slight advantage in using the low flashpoint dangerous goods material, but it's really outweighed by the advantages of the much more safe liquid, e.g. 309. And for most applications, 309 is perfectly adequate. There are several publications about it. We can look it up and send them the references.
Of course. Excellent. Yes, definitely do get in contact with us, Neil, if you would like those publications. I actually have another question from Susan Smith asked about liquid scintillators. She was wondering if there is a change in the efficiency or performance when the liquid expands, referring, I think, specifically to the newer liquids here.
Well, if the liquid expands, of course, the density changes a lot, but I don't think this makes a huge difference in sensitivity. Actually, I never read about this being an issue. But of course, when the density changes, the proton density probably changes also a little. I don't think it has a very big effect.
All right. And then I have a question here from Rakesh. He gives the context that the liquid scintillators like BC501 are very efficient and so are still being crystals. What he's wondering in particular is, from the perspective of neutron gamma separation, which one of those materials is more efficient?
The best neutron gamma separation actually is achieved with still beam crystals. It's way superior to all liquids. Unfortunately, it's a little more expensive and it can be made in real large dimensions, but the separation is really outstanding.
Excellent. And he actually did have a follow-up question on still beam, which is, what is the biggest size produced so far? And if you could possibly comment on the FOM using conventional analog electronics in the act of moving over to digitization.
That's a good question. Actually, the largest size on still beam crystals, I think, is about 5-inch. I'm not totally sure that there may be some new developments for larger pieces, but practical, I think 5-inch. There have been an extensive comparison between figure of merits measured in digital and analog ways. But as I said, it is extremely difficult to compare just straight numbers like that. But it is doing pulse shape analysis with digital techniques requires a different approach than in the analog way. So I think the future is actually into digital electronics, and we don't have much choice because the analog electronics is just simply dying out.
Okay. Kind of pivoting over here to a different topic. Grant Goodyear was he mentioned that Reuter-Stokes is doping sodium iodide with lithium-6. Is there anything similar that you've done?
Yeah, that is true. That is a material, a lithium-doped sodium iodide crystal is one of the other options. I didn't touch into that. We didn't venture into that material, but it's definitely an option. That is true. Yeah.
Excellent. Rakesh had another question here, reading them in order. He's mentioned in context of the digitization that Zercross and charge comparison are two main pulse shape discrimination techniques. Do digitizers kind of opt those in?
Well, digitizers have a different approach. You also set their windows in the time domain. But actually, it's a little outside my expertise to comment on that. I find it difficult to compare. I don't know.
Right. definitely feel free to follow up with us, Rakesh, and we'll
Yeah.
try to get you what information we have and supporting documents and other terms. Moving on to a question from Harold Specter. He comes from the perspective of nuclear criticality safety. He's wondering about suggestions for InSight neutron detectors to use prior to excavation for a variety of special nuclear materials. Would there be an optimal neutron detection material for that?
That's a rather complicated question. I actually would need some more details to answer that question. Because I didn't catch the first part of the question. Maybe that is something really to write down in an email. We can look at it carefully, and I definitely think there is an option there in the scintillation solutions, but I would need more details.
All right, Harold, please feel free to reach out to either myself or Paul. Let me go ahead and actually go to the end of the presentation there that has our emails. Or I guess just ours, but yes, do feel free to reach out and we will get you the specific information that you need. Let's see, what other questions do we have? All right, so from Haluk, he is wondering if you think, sorry, the question jumped. I have to scroll back up. Do you think that lithium fluoride -ZNS AG scintillators can be used together for monitoring cargo flow in seaports/airports for like as radiation portal monitors due to the current shortage of helium-3?
Yeah, definitely. Yes.
Oh, awesome. And Yujuan is asking about the ratio between bromine and the lanthanum effect on the performance of CLLBC.
The ratio between bromine and what?
Bromine and lanthanum.
And lanthanum. I think that ratio is fixed. The ratio between bromine and chlorine can vary a little. That is something you can still, because CLBC, there's also a material called CLLB, which we don't work with, but because CLBC, bromochloride, has actually a better energy resolution than CLLB. Because of reasons not really known to me, but so that I don't think you can change the ratio between the bromine and the lanthanum so easy in this material. That's pretty well fixed, I think, in the lattice.
Excellent. Okay. And real quick, Bill, thank you for attending. I will be in contact with you regarding those best options for neutron detection, neutron detectors for portal monitors. And here's a question from David Weaver, Paul. He is asking if high-pressure helium-3 detectors are effective for space applications, or do you feel there would be a better solution in that context?
With helium-3 applications for space, I never heard about this, but I think a pressurized tube in space, I would definitely go for a scintillation solution read out with silicon photomultipliers, because then you need no high voltage, less power, and power is important for space.
Okay.
So if I would have to design right now a thermal neutron detector for space, I do it with the scintillation option.
Excellent. And now I have kind of a broader question. Rakesh, who's asked several questions, is wondering if there might be a talk on detection particle detectors, alpha, proton, for instance, like cesium iodide detectors. He's wondering if we might be doing a presentation on that in the future.
We can always think about doing it. We're familiar with the material. We know how to reconstruct things regularly. Yes.
Yeah.
Thanks for the suggestion. Thanks for the suggestion anyway.
Yes, thank you.
Yeah.
So this question is from Ramesh, and he is wondering about if you would yourself know of any specific model names for neutron detectors that do personnel dosimetry. Would that be anything you have knowledge of, Paul?
I don't know directly. I have to think about this question. Sorry. Phrase it.
Yeah,
dosimetry depends what kind of dosimetry you're thinking about. If it needs to be something wearable, then it's a different story. Then it's more an instrumentation question. When I'm talking about sensors tonight, I have to think about it.
Of course. All right. Excellent. And definitely feel free to get in contact with Berkeley Nucleonics as well, Ramesh. We can do equipment recommendations. And I have a Question from Marie. Thank you for attending the presentation. And she is wondering if, Paul, you could elaborate on the use of SiPms instead of PMTs for different scintillators.
Well, we have a whole webinar dedicated to that, remember?
So
I think it's available on YouTube. There we discussed the option of a SiPms replacing scintillator. But when I focused on what I told today about pill shape discrimination, as long as the scintillators are not too large, you can definitely do pill shape discrimination for neutron gamma separation using SiPms instead of photomultiplier tubes. If you need a very large number of SiPms because the scintillator is so large, you're affecting the speed of your scintillator and this affects your time response. Then it becomes more difficult. But definitely for a small scintillator that you use now with a photomultiplier tube for neutron gamma discrimination, you can do this as well with a SiPm, yes. And the general question is more addressed in the other presentation, I think.
That is correct. We definitely do have a further webinar on SiPm detectors. I'm going to go ahead and drop the link to our YouTube channel. That will have the archives of all of our presentations. We also do presentations in RF instrumentation and precision timing technologies. And moving back to the questions, though, it looks like we have about 5 minutes left in kind of the planned time. So I'll go ahead and maybe take 3 to 4 more questions. From Jonathan Folkerts, I have, are you familiar, Paul, with how the gadolinium is loaded into the liquid scintillators? And ensuing from that, is it possible to load other middles for neutrino detection rather than neutrons?
Yeah, that depends if the materials are available in metallo-organic forms. So gadolinium is loaded in liquid scintillator in forms of a organogadolinium compound, so far I know at least. The question is how stable you can make this particular compound that doesn't precipitate out of the liquid in time, like we had one occasion when you go higher than 1% in gadolinium loading. We saw already that there is boron loading of liquid scintillators that is around. On the other hand, you cannot load any material in a scintillator just like that. You have to find the proper organic metallo compound. So it's more a chemical question, and I know this is one of the subjects I touched in the beginning, that there's a lot of research going on at the moment in finding new scintillators with loading, just like we try, for example, to load organic scintillators with bismuth to give them some photofraction to do pulse rate discrimination, pulse height discrimination with organic materials. So there are definitely people looking into this matter. There's also a research activity by trying to load nanoparticles in liquid scintillators and in plastic scintillators. This is all things, work in progress, and we hope in the future we have a material we can offer to the community to use in our sensors.
Okay, great. And then kind of moving from that into something fairly theoretical, Faiz is wondering, how much should we be hopeful to use these detectors discussed in the presentation in the search for dark matter in the near future?
Whoa, that's a very generic question, dark matter research. I think there are many materials used in dark matter at the moment. Some scintillators are, but I don't think that touches the subjects I discussed today.
He mentioned it would be for the exclusion of neutron signals and as a detector for WIMPs.
WIMPs, yeah. I never thought about that. Should think about it, I don't know. Dark matter research is a very specific topic, and there are several materials used in this respect, also some scintillators. I don't know.
All right. And I have Robert Wilson asking, not specifically related to neutrons, but is there an air equivalent scintillator?
Air equivalent?
Yeah.
A
typo there, yeah.
I know a tissue equivalent, a plastic scintillator. With air equivalent, that means that it should have a very low density. I think air has a very low density, isn't it? So I think scintillators have much more density than air. So I would say that you deposit much more energy in a solid material than in air. So I don't think so.
All right. I think with that answer, we're just kind of running on to the end of the presentation here. I would like to kind of thank everybody again for attending, as well as for the questions. We definitely hope that you will attend our next webinar in the field of neutron detection.
Thanks for listening.
Of course. Thank you very much and have a nice day.
Bye.